Hi Bobcats. In this video, we're going to start the connection between thermodynamics and equilibrium. We're going to see the thermodynamics behind why some reactions stop at an equilibrium mixture instead of going all of the way to products. And we're going to see how you can calculate the delta G when we end up in one of these non-standard conditions. So our objectives are to look at this equilibrium mixture of a reaction and to calculate the delta G naught at these the delta G at non-standard concentrations. Just to refresh your brains a little bit as we compare thermodynamics and equilibrium. Thermodynamics were in chapter 15 and chapter 18. Notice an error here, that should say chapter 18, not chapter 19. And our original study of equilibrium, which was back in chapter 15, if we manipulate the equations of our reactions, we have to manipulate our value for the thermodynamic values, delta H, delta S, and delta G. So for instance, if we multiply all of our coefficients by a constant, we'll multiply the thermo value by that same constant. But for an equilibrium constant, we would raise K to the power of that constant. In thermo, if we reverse a reaction, we change the sign of the thermo value, but in equilibrium, we take the reciprocal of K. And in doing things like Hess's law type problems, if we add two reactions, we add their thermo values, their delta H's or delta G's or delta S's. But if we're talking equilibrium constants, we would multiply the equilibrium constants. Okay, in this slide, we're going to explore the thermodynamics argument for why certain reactions reach an equilibrium instead of going to completion. And we're going to do it with a very simple reaction, which is the blue reactants in equilibrium with the purple products. And we tend to draw energy level diagrams like this. The particular energy that we're looking at is the Gibbs free energy, and the horizontal axis is sometimes referred to as things like the reaction coordinate or the reaction progress. If we're all the way over on the left, we have nothing but reactants present, and that's why that circle all the way over to the left has just blue molecules in it. If we move all the way over to the right in this diagram, we have all products, and that's why the circle that's all the way to the right has just purple molecules in it. But this particular reaction actually reaches a minimum in its Gibbs free energy right here. At this point, I'm making an X on. So that minimum, that lowest possible point for the Gibbs free energy occurs not for reactants, not for products, but for a mixture of reactants and products. It is a fundamental driving force in nature to go to the position of lowest energy. Sometimes an analogy that's used for this is, imagine that this is the slope of a hill, and you released a ball somewhere up on the hill. Well, it would roll down to this minimum because it's being pulled down by gravity. Well, other types of energy also want to minimize, and the Gibbs free energy for a reaction wants to minimize. So that lowest possible Gibbs free energy is obtained when we reach an equilibrium mixture of both reactants and products. And so that's why some reactions reach an equilibrium instead of going all the way to reactant or staying all the way at reactants or going all the way to products. It's just in their nature to have a lower Gibbs free energy as that equilibrium mixture. Okay, so what about our equilibrium constant and our Q and all that sort of stuff? Well, let's say we haven't given this reaction enough time to reach equilibrium. And let's say that on this diagram we were somewhere over to the left of our equilibrium position. This is when K will be satisfied, or I guess we could say Q is equal to K at that equilibrium position. Well, what if we're somewhere over to the left and we have more reactants than we would have at equilibrium? We have fewer products than we would have at equilibrium. That means that Q would be less than K. So in the scenario where the reaction has not reached equilibrium yet, and we find that we are in the scenario where Q is less than K, there is a driving force for this reaction to go in the forward direction to reach equilibrium. So in this scenario, the reaction would be spontaneous in the forward direction until enough reactants were converted to products so that Q equals K and we would be at equilibrium. Well, what if we're instead over in this position to the right of equilibrium? And at this point, Q would be bigger than K. When we look at that ratio, we would have more products than we should have at equilibrium. We would have fewer reactants. So when we're over in this regime, there's a driving force to reach equilibrium, which makes the reaction spontaneous in the reverse direction. Sorry, I'm trying to write and talk at the same time and not doing a very good job. You can't even read that. Let's say reverse. Spontaneous in the reverse direction. So if we're in the scenario where Q is bigger than K, the thermodynamics pushes the reaction in the reverse direction until enough products have been converted into reactants so that Q is equal to K. So that's kind of the thermodynamics argument behind why some reactions will reach an equilibrium mixture instead of going all the way to completion. The bottom line is that that equilibrium mixture has a lower Gibbs free energy than the plain products would. When a system is at equilibrium, let's see which one of these statements best completes the sentence. The reverse process is spontaneous, but the forward is not. No, the forward and reverse processes are both spontaneous. All right, so this gets to be a question of semantics. I want to make sure that you understand the way chemists talk about this. I'm just going to go ahead and tell you what the best answer on this is. The best answer is that the reaction is not spontaneous in either direction. Yes, the reaction does continue to take place in both the forward direction and the reverse direction at the same rate. So there is no overall shift in the position of the reaction. So when we say that the reaction is spontaneous in the reverse direction, we mean it is spontaneous for products to be converted to reactants, net, overall. If we say it's spontaneous in the forward direction, it is spontaneous for reactants to be converted into products, net, overall. Once we have reached equilibrium, even though the reaction is still going in both the forward and reverse direction at equal rates, there's no net change. And so the best answer to this question is that at equilibrium, the process is not spontaneous in either direction because none of the concentrations are changing.